stability, right? Remember, this goes back to Dijkstra's thing that I introduced you to last class, right? If you look at the maps in India of distance maps, right? You want to know distances from different places. They always list them in a nice table. So that way, let's say you're planning a car journey. Let's say you're starting in Kakinada, you want to tour the entire Andhra Pradesh after the break, right? And then come back. So you have to figure out the shortest paths from one place to other place, so that way you can plan your journey accordingly. Okay? Very practical application, the road network as we call it. Okay? And routing of traffic, like traveling salesman problem. So all of those things rely on the shortest, all pair shortest path. The solution of which was given by Dijkstra. So we'll take a look at that one more time today. Okay? Okay, let me move. For those of you who joined late, we started off with that quote about excellence. So keep that in mind as you progress in your career, students. Excellence is a habit. Actually, that applies not only to students but to all of us faculty members, right? We should do the best that we can for students. Okay. Just a quick review, as always. So why use graphs, right? These are all the examples of where graphs are used. Road maps, airline route. In games, we use that. Okay. If you are into electrical engineering and printed circuit boards and all of those things, design of PCB. Okay. Same thing with internet. Okay. Pages on a web. Students and courses, you name it, it is there. Graphs are all over the place. Okay. We looked at the graph traversals, right? You have the depth first search where you go all the way down first before going off to another branch. And then whereas breadth first is you go to each level, you traverse all the nodes in a given level and then go to the next level. Okay, we did that. Okay, now Jntuk Kakinada is slowly coming into play. They have a new audio system and all that, so they were having some difficulty with their audio, but I see all of them now. Okay. We also said that we use either a stack or a priority queue. In the case of depth first search, we said that we can use the stack, and when we use the stack, we can keep track of nodes that are to be visited next or nodes that we have already visited. Okay. In the case of depth first, we call it aggressive because it examines the complete path, meaning it goes until it either reaches the solution or it reaches a dead end where it has to backtrack. Okay. Same thing, we also can also use queue to keep track of nodes to be visited or nodes that we have already visited. And then in typically breadth, we use queues in the case of breadth first search algorithms. So it's called cautious algorithm because it examines every path of length I, meaning level, every node at the level before it goes to the next level. Okay. Dijkstra's algorithm uses the breadth first search. Search is everywhere. Games, trees, mazes. You know mazes, right? How to navigate a maze. DFS explores a few possible moves looking at the effects far into the future, whereas BFS explores many solutions but only sees in the near term. So depending on the context, right? Remember I had a little bit of discussion between which one to use, right? It really depends on what you're trying to achieve, right? So the problem space dictates whether to use breadth first or depth first. In the case of finding shortest paths, distances and things like that, you use breadth first search. In the case of things such as games like, remember I mentioned the 8 queens problem. Most of these games, they use depth first search. Okay. Let's look at Dijkstra's algorithm. Single source shortest path problem. Problem of finding the shortest path from a source vertex V to all other vertices in the graph. That is what we have done, right? The exercise was that. Except you came up with an informal algorithm in your head, right? But Dijkstra has actually come up with a formal solution to that. I don't know if I mentioned this to you or not. This entire shortest path problem by Dijkstra, apparently he came up with the algorithm in a cafe when he was sipping coffee or something like that in 15 minutes, all in his head, how that should be solved. And then it was 100% accurate. He did not even write it on a piece of paper when he solved it in his head. And it was perfect. As I mentioned to you, these are all the different types of applications. Maps, all Google Maps uses that, MapQuest, all your GPS stuff, they use that. Okay. You see example of routers, those things are computer networking, right? So they use those algorithms. So how does he solve it, right? Again, the idea is not to make you experts in that, but just a little bit of knowledge on that would be helpful, right? First of all, there are some constraints, right? It can work on both types of graphs, both directed as well as undirected, but all of them should have non-negative weights. If you have negative weights, it doesn't work. So there are other people who have considered negative weights and modified Dijkstra's algorithm for that. But the fundamental Dijkstra's algorithm works on non-negative weights. So what is the input to solving the problem? The input is a weighted graph, right? The graph is nothing but vertices and edges. And then you are given the source vertex, because you are calculating these things from a source vertex. Okay. The output is the length of the shortest path from a given source vertex V to all other vertices. That is exactly what we solved in the sample that I gave you at the beginning of the class. So what does the algorithm do? It computes for each vertex U the distance to U from the starting vertex. Okay. Now, while it is computing those things, the algorithm keeps track of the set of vertices for which the distance has already been computed. Okay. So you call it like you're putting it in the cloud, nothing but a file, right? You have some kind of a data structure, you're saving that. Hey, I'm done with this particular vertex. So let me move on to the other one, right? So he keeps track of every vertex with a label D. D stands for distance, right? For any vertex U, du stores the approximation of the distance between V and U. Remember, V is the source vertex. Okay. So the algorithm will update the du value when it finds a shorter path from V to U. Okay. So once you add a vertex U to the cloud, its label du is equal to the actual final distance between the starting vertex V and vertex U. So what does it mean? That means you have found the minimum distance to a given vertex. So in our example, when I said start to one node 1, you had a distance of 3, right? And then, visually you just saw that 1. In theory, you could have gone by 2 to 1 to if there was a node there, right? Depending on how the graph is, right? But the moment you determine that is the minimum value, you push it to the cloud, and that that particular answer would not change again. Okay? That's what that last fourth bullet point means. Okay? So here is some pseudocode for Dijkstra. For each vertex V, to begin with, you are initializing to infinity. Okay? So you can, I will not go through the full thing here, but intuitively, you are initializing all the things first. Okay? And then list has all the vertices. While list is not empty, you are getting remove list vertex with minimum distance. Okay? So once it is known, okay, mark V as known, meaning because that is the source vertex, right? That is the reference point. Okay? And then for each unknown neighbor of V, in our case the V was the S, remember the S, node S. Okay? So you are going to calculate the distance from V's distance plus edge, because you are basically adding up the weights, right? Okay. Now while you are doing that, if you find a value smaller in that given path, you make that as a new route. Okay? So if you notice one thing here, reconstructing the path from vertex 2 back to V1 based on the logic here that is stated here. Okay? I don't know if in the exam you'll be asked to write. So here is one similar example that we, based on the exercise that we did, right? So everything is initially marked infinity because you don't know what the shortest paths are. Okay? All vertices except the source. Okay? The source here is A. Okay? Now once you are there, notice one thing, all the distances, remember that this is the distance labeled D, right? So they are all marked infinity to begin with. Okay? Notice these things that are highlighted here. Okay? This is basically a trace of the algorithm. Okay? So now you are updating the neighbor's distance. Okay? So B to A to B is 2, right? So you know that. Okay? That's the neighbor of A because there's an arrow going from A to B. Okay? So that's why that's the neighbor. You don't, and then there's an arrow going from A to D. Okay, see the arrow there, it's a directed edge, okay? We're not talking about undirected graph here, we're talking about a directed graph. So you're updating D to 1. What else you updated here? That's it. Nothing else you updated. Okay? Because those are the two neighbors of A. C is not a neighbor of A because you cannot go from A to C. In a directed graph, the arrow tells you whether you can go or not, right? Okay, so A to C, it's not a neighbor, even though visually it looks like a neighbor, especially if you remove the direction, then it is a neighbor, right? But since we have to use the direction, two neighbors of A are B and D, and then you know the distances, you put the distances there. Okay? Now let's see what happens in the next slide. Pick vertex with minimum distance, this is D, right? Out of those two, what is the minimum distance node that you have? D. So you pick vertex in list with minimum distance, that is D, okay. I'm going to pick that. Okay. Now you're updating the neighbors from D. Because remember, what we are trying to do is, from A, I want you to follow this carefully. From A, we need to find the distance to all the other nodes, right? To do that first, from your starting point, you can achieve that goal only if you pick the neighbor with the lowest weight, correct? Common sense, right? If I go via B, obviously, if there's a shorter path where I can go via D, obviously I won't get an optimal solution. That's the reason why you pick the lowest neighbor first. Okay? That's the way. If you see on the left here in the slide, you can see distance C, 1. 1 meaning all of them are going to go where? D. And then from D to C, you see the arrow there, right? That is 2. So you add D plus, D is 1, 1 plus 2 is 3. You get 3 there. Distance to E, because D to E there is an arrow, the blue arrow. Okay, 1 plus 2 is 3. Distance S, 1 plus 8 equal to 9. Distance G, 1 plus 4 equal to 5. Okay. So pick vertex in list with minimum distance B and update neighbors. Okay. So that's why did we pick B there? Distance C. G, okay, got it. Okay. Pick vertex in list with minimum distance B and update neighbors. Okay. So then you pick B, and then you are updating the neighbors again. So you finish the 1, you finish now with B, you compute the same thing. Okay. So like that, you apply the algorithm. Okay. I'll not go through each and every slide for that. I want you to trace it and convince yourself, because I gave the algorithm and the visual there. Okay. So at the end of it, you would get the all pairs shortest distance from vertex A. Okay. There's a second example that I gave you here, which is similar to what you have done. Right? So we'll do this as like a exercise in the class later in the class. Okay, hold on to it, where I'll make you go through the algorithm and apply and do the trace formally. So that way you get a comfort feeling. Okay, everything is given there for you. Okay, you just have to trace it and convince yourself. Now, we don't talk too much about the time complexity other than what you have learned, but when we analyze it, you can see here the time complexity for Dijkstra's algorithm here, especially when they're dense graphs. Remember, dense means many edges. And by the way, we use adjacency matrix, right, for dense graphs, and adjacency lists for sparse graphs. So your complexity is measured in terms of vertices and edges. Initialization to infinity is the order of V, right? Because how many vertices you have, we have to do that. And then for each of those vertices, you have a loop. Okay, so he does some computation, and you can see the total time taken is the order of V squared plus number of V. Now, higher order terms is what we focus on, ignoring the lower order terms. Okay, that's why it becomes order of square of the number of vertices. Okay. Now, if you were to do that using queues, okay, if you use queues, it's implemented more efficiently, as it says here. And then if you study the complexity there, it's of the order of log of V, basically, right? E, order of V times log of V. Now, taking the higher order terms, basically it comes to an order of V, which is significantly better than the order of V squared. Okay. Let me pause here for a second. Questions, comments? Very useful, and you will do the exercise too using the Dijkstra's algorithm, okay? I wanted to finish the lecture first before I let you do those things. Okay. Now, in the process of trying to figure out all these distances and things like that, to solve the problem related to graphs, what we do is we build what are known as spanning trees. Okay. So we'll take a brief look at spanning trees, and then there are a couple of good algorithms related to spanning trees. We'll study them too. Quick overview, not even really study, right? So here is a justification for why we need to do these things. Okay. Whatever we learned is a practical application, right? So let us consider this example of problem of laying a telephone wire. So you have the central office here, and then you have to put a wire. Otherwise, you don't get connectivity to home, right? So one way of doing it is connecting from the central office to each of the houses. Does it look like a tree structure to you? It does, right? Now, when you do it like this, the problem is, right, it's like a dedicated thing here, and then you're using too much wire, and that means more cost, okay? Cost of installing, cost of maintaining, all of those things, okay? By using the concept of spanning trees and all these shortest paths and things like that, we can minimize the total length of the wire connecting the customers. Much less wire is used here, see, instead of dedication line. Now, how do we come up with these types of architectures? That's where the graph theory and the spanning trees and all come into play. Okay. While still retaining a connection between all the vertices in the component. Okay. Now, when we studied trees, right, we also studied this concept, like if there are n vertices, the tree would have n minus 1 edges. Same thing applies here too. Okay. Forest is when you traverse all vertices of an undirected graph. Okay. Let's not worry about the spanning forest now. We'll only worry about the spanning tree, because ultimately our goal is to come up with what is known as the minimum spanning tree. That gives you the optimal shortest units of whatever, whether it's time, distance, wiring, whatever you want to call it. Okay. Some theory there. Let me skip that. So what we are basically saying here is, when you have a connected undirected graph, okay, every node is reachable from every other node. Okay. Undirected, of course, you know, that means edges do not have an associated direction. Okay. And then when you draw a spanning tree for this, how would it look like? Okay. These are all the various spanning trees, because the definition of a spanning tree is how you can traverse all the nodes, basically, right, of a connected graph. You can see how many different spanning trees are there in this case, right? 4. Okay. Now, by the way, in case you're saying why there are 4 and all that, there's actually a lot of mathematical theory and proofs and all as to see how many spanning trees can come in an n vertices graph, which is fully connected, or how many edges it has. So there are all kinds of mathematical analysis done on spanning trees. Not interested in that at this moment, but when you go deep, then you will learn all those things. The question is, how do you find a spanning tree, right? So there's some algorithm here. Okay. So you pick an initial node and call it part of the spanning tree. Then you search from the initial node. Each time you find a node that is not in the spanning tree, add it to the spanning tree, both the new node and the edge you follow to get to it. Okay? Because you need to cover all of those things, right? So here is one undirected graph that is given to you. So using a BFS search, he is able to come up with a spanning tree. Remember, it should be a tree, it's not a graph. What is the difference between a graph and a tree? Graph can have cycles, trees cannot have cycles. Okay. Here is another way of coming up with a spanning tree using a depth first search from the top. Different types of trees, right? Depending on whether you are using a BFS or a DFS. Okay. So why do we do all of those things? Bottom line is you want to minimize costs. Okay. So here is an example that the author has given. You want to supply a set of houses, okay, with power, water, sewage lines, telephone lines. Okay. So the way you correct them is you are using a spanning tree. I think you should go and ask those civil engineers, or I think it's civil engineers to do all the houses in India, right? You should ask them, do you use a spanning tree or how do you do that? My gut tells me those guys probably don't apply all these concepts. They probably do it by seat of the pants, right? And I'm not sure if they optimize it. You have to tell me how they work. But I can tell you in US for sure, these concepts are used. Okay. Okay. So as it says here, right, to reduce costs even further, you could connect the houses with minimum cost spanning tree. Now, you cannot come up with a minimum cost spanning tree unless you use all these all-pair shortest path and things like that. That's where these things come in handy for you. Okay. So what is a minimum cost spanning tree? So you are assuming that you have connected under a graph with some kind of weights associated with each edges. Okay. And the cost of the tree would be the sum of the cost of its edges. Right? You have the edges there, the edge weights you add up, that's the sum of the cost. So a minimum cost spanning tree is then a spanning tree that has the lowest cost. Okay? So how do you come up with a minimum cost spanning tree? Here is a connected undirected graph. The weights show the numbers. This is the reason why I made you do that, right? So if you know how to connect all of these edges with the minimum cost, that means you're basically adding up all the edge weights, right? Similar to what you have done in the exercise. Okay? As you can see how all of them are connected in the lowest cost, like a minimum cost spanning tree. Okay? It's easier said than done, okay? Once you do some practice examples, you will understand that. How do we come up with that? That is the key thing, right? It's visually for a small diagram, yeah, it's easy, right? But how do we come up with that, right? It's a classic computer science problem. Two most famous algorithms. The faculty members here would know these things because they probably teach the advanced course too, right? Kruskal's algorithm and then Prim's algorithm. Okay. So fundamentals of Kruskal algorithm is initially there is nothing in the spanning tree, right? You're always adding the cheapest edge that does not create a cycle. Okay. So that means he's basically building a tree of all the edges. That's what Kruskal's algorithm is. Okay. Whereas Prim algorithm consists of both edges and nodes. Okay. Whereas you start with any one node, anything, it doesn't matter which one. And then from that reference point on, you're repeatedly adding the cheapest edge. And the node it leads to, because edge is connecting nodes, right? Condition being the node should not already be in the spanning tree. If the node is already in the spanning tree, if you're adding it, then it creates a cycle. Then it's no longer a tree. Okay? Very high level here. Okay? So here is a Kruskal's algorithm. Okay? So you start with empty spanning tree. You already know all the edges of the graph. And you already know the number of nodes in the graph. Okay? And you already know the property that when you draw a tree, if you have n number of nodes, there will be n minus 1 edges. That's the reason why you see while t has fewer than n minus 1 edges. Okay? So you remove an edge, VW, V is the vertex and W is the weight of the edge, right? Of the lowest cost from E. Okay? Now, while you're adding it, if it creates a cycle, then you discard it. Otherwise, you add it to it. Okay. Now, how do we find these edges? The easiest way is finding an edge would be you can sort all the edges. You learned all the sorting algorithms. Use one of those things, sort all the edges. Okay. Now, whether we have a cycle or not, as you can see the last bullet, right? Whether it forms a cycle or not, there's another algorithm here, of course, which is not covered because these are all not easy algorithms, right? The basic idea is it's an edge-driven technique. Okay. Now again, if I'm going fast, there's a reason, because I don't think this level of detail is what your syllabus is asking. The syllabus is saying explain the concept. The concept is all pairs shortest path, and the concept is tree. How to draw a tree from the graph. Okay? But how to come up with a minimum spanning tree, then that is where you apply these algorithms, Kruskal's and Prim's. We actually go through C program for these algorithms in that class. So here is Prim's algorithm. You still have a spanning tree. You're taking a single node to begin with. Then this is similar to what we do in Dijkstra, right? We start off with a reference point, and then you start looking at the adjacent nodes. That's what E equal to this one. Okay. And then while the tree does not contain all the nodes, you remove one edge of the lowest cost from E. Okay. And that weight is already in T, then is discarded. Otherwise, you add the edge and the node W to T. Okay. And then you continue adding to E. E is the set of edges, right? The edges adjacent to W. Okay. And then this is a breadth first algorithm basically. That's why an edge of the lowest cost can be found with a priority queue. Testing of a cycle is automatic. Okay. Because the way the algorithm is designed, you would not encounter cycles here. That's why it's much easier to implement Prim's algorithm. Okay, so here is a nice illustration of generating a minimum spanning tree. So how did we come up with this? What is the difference between the left and right? The red are the one that we are, so A to D is 2. I do not know how he has come up with that. Maybe I have the illustration here. Let's see. Okay. So you are given the graph on the left, and then you come up with this tree here. Okay. Let's see how it traces. Pick a vertex R to be root. Okay. He has given some algorithm here. Set dr equal to 0. Okay. Parent of R, because when you pick a vertex, it means, remember it's a tree. Tree should have a parent. Parent R equal to null, because you're starting from the starting point, right? That is the root. There is no parent to the root. And then for all vertices, V not equal to R, you are initializing it to infinity. So here you have A, B, C, D, E. You're taking E. Remember, you can pick up any vertex, right? So you're taking E. Okay. The distance of R is 0, because it's E to E is 0. You're right there. And for all the other nodes, that is step number C, okay, for A, B, C, D, you are making them infinity here, as you can see in the table here, okay. The vertex that you have picked is E, one more time. You make the distance of E to E 0, and to all other nodes, you make infinity, okay. While P is not empty, select the next vertex U to add to the tree, okay. And then, of course, you're updating the weight of each vertex adjacent to U, which is not in the tree. Okay. Looks easy to say, not easy to code and all that. That is what he has done here, all right? So he has updated the distances to B, C, and D, okay? So we are updating from vertex E the distances and parent for its adjacent vertices. So when you take E, the adjacent vertices are B, C. Okay. A, you leave it infinity because A is not adjacent to E. The only thing that's adjacent to E are D, C, B. And you're looking at their weights here, which are 4, 5, and 5. A is infinity. Okay? Again, these things you cannot understand unless you trace it. Okay? I realize that. I'm just giving you an overview, and then you will do some practice problems, right? And what is the parent of B, C, and D? Parent is E. That's why you see in the table, you have chosen to put the parent there. Okay, then you continue like that, follow the algorithm, and then you fill out the entire table. Okay, that's what I've given you, the traces there. Okay. So then you get the final minimum spanning tree, which is, if you look at E, okay, E, D, B, and D has the children A and C. So that would be the tree, where E is the root. Okay. So from the root you have 2 children B and D, and then from D you have 2 children A and C. Okay. Here about Prim's algorithm, right? Because whenever you're adding an edge, you're always adding it which is the minimum among all edges. Okay, so that's the reason why at the end of the cycle you will get a minimum spanning tree. Okay, and then once you add all the vertices, you have a minimum spanning tree for the full graph. There's another way of doing it. I mean, this is not getting into too detail. I put the slides, but we will leave it like that. That is the Kruskal's algorithm. Okay, how we create it, I gave you the same illustration. And there's an algorithm, and then I give the trace how it is done. Okay, you just have to go do this trace yourself. Okay, I'll give time in the class after I'm done with this. Okay? So in the case of Kruskal, what happens is every tree is in the forest. Okay, it is connecting the vertices, and once all vertices are connected to one tree, it stops. So slightly different approaches. Now, why are they in the just like the Dijkstra's algorithm? Both these algorithms are called greedy algorithms. Okay. Why it's called a greedy algorithm? Because when you have a reference point, you're always looking for the shortest distance. When I'm using the word distance, it could be lowest cost, right? That where distance, cost, time, whatever is the lowest number. Okay? So the entire approach is called greedy because you're always looking for a shortcut. Okay? Once you take my advanced class, you would see that the greedy approach does not work always. Okay? There are lots of problems. We actually do some examples and exercises and things like that where I show that greedy approach does not work for a lot of problems. You can do some research on your own to see what those are. Maybe next class I'll show you some examples where to set you up for the next advanced class. I will show you some examples as to where the greedy approach does not work. Okay, let me stop here. Questions, comments? The class is very silent. Are you all sleeping? Or are you all lost? These are kind of things where unless you do it, you will not know, right? I understand that. Okay. There's one more topic that I wanted to cover, and then we'll do some practice, okay? the topic is called transitive closure. Okay, this is another topic. If you look at the syllabus, it is one of the last topics actually. I'm pretty much done after this, right? Let me put it in. Okay. So what does transitive closure mean, right? If you take a graph, right? A graph has vertices and edges, correct? So from that, you create another graph. That's why it's called G star, where you have vertices and then you get some additional edges. Okay. These additional edges corresponds to the scenario where there's a path from vertex I to vertex J. Okay. What does it mean, right? Let me put it here. Give me a second. So what the transitive closure of a graph is a list of edges for any vertices that can reach each other. Okay. It doesn't have to be connected to one vertex, all of them, as long as there's a path. That's what a transitive closure is, right? So if you look at this one here, I don't know if you can see the numbers here. I should have the numbers here. Again, let me do it. I don't want to be sloppy here. Sorry about that. I should have caught this before the class, but I can do it here, no problem. Bear with me for a second. Okay, I have it all done. So here, if you see the graph on the left, right? So you have these nodes 1 through 8. Okay, 1 to 5 is connected, 2 to 1, right? So if you see the edges that are connected, you have 1 to 5, 2 to 1, 4 to 2. That's the table that you see here, right? 4 to 3 is connected, 6 to 3 like that. So now you want to find the transitive closure of this graph. Okay. So if you look at the graph here on the right, the numbers are same there. I did not make them in black again. It's the same figure. But now you can see some new things got added here, right? Like, for example, you are able to reach from 7 to 3. Okay, how you are able to reach from 7 to 3? See that light line there that you have there? Let me make that dark here for a second. Okay, how do I make that dark? I need to go to format shape, color. I'm not able to do the editing here, but do you see that light line there from 7 to 3 in the graph? If you do, then I don't have to worry. Okay, color, compound type, joint type. There it is, color. Let me make it like dark blue. Okay, yeah, see that one there? And then this one, let me. Yeah. And then this one more color. Let me change it, then you will be able to see those things. Okay, I have it here. back into presentation mode. So I changed some colors here, right? See this dark blue and all of those things. So transitive closure means basically you are given a graph. Okay, this is a legitimate exam question for you. Okay, so you have to highlight all the other paths that you can go to. So in this case, if you see this 7 to 3, I put an arrow. Was it there in the original graph? No. Okay. We are saying, hey, from 7 there is a path to 3. So that belongs to transitive closure. It's actually a standard mathematical concept, and you learn more about these things in databases too. It's like, when there's a path from A to B, and there's a path from A to C. No, sorry, there's a path from A to B and B to C. Then you know that you can go from A to C, right? That's what transitive closure is. Meaning, hey, I know I can go to B first, and from B to C I can go. That means I can navigate from A to C. That is what the 7 to 3 is, because the way you get to 7 to 3 is how, just because you drew the arrow does not mean there's a direct path, okay? That's not what we are saying here. What we are saying is, hey, from 7, there's a way for me to go to 3 via 8 and 6. Right? I can go from 7 to 8, 8 to 6, and 6 to 3. Okay. Same thing, from 8 I can go to 3. From 7 I can go to 6. Okay. There are some other arrows that are listed here on the top part of it. I will change the color of that before I post it. Okay. So that is what transitive closure is. It's nothing but the list of edges for any vertices that can reach each other. Okay. That's very important, right? When you are mapping your routes to travel, you need to find the transitive closure of a graph, and then once you know the transitive closure of a graph, it in turn allows you to find out the distances, right? And then you always come up with a minimum spanning tree to say, okay, this is the best route for me to take to navigate all the nodes. Okay. So here is another second take on the same thing about the transitive closure, explained through an adjacency matrix, right? So if you look at the graph on the left, 1, 2, 3, and 4, right? You see the diagonal, the way the author defined here, you can put a 1 in the adjacency matrix if either I equal to j or if there is an arrow there. So if you look at the table A, adjacency matrix 1, 1, A11 cell, that is this one, right? 1, 2, 3, 4, 1, 2, 3, 4, right? So A11 is 1 because I is equal to I and J are 1 and 1. You put a 1. Continuing on the 1, node 1. If you continue from 1 to 2, there is an edge. That's why you put a 1 there. Is there an edge from 1 to 3? The columns are 1, 2, 3, 4, by the way, on the top. And the rows are 1, 2, 3, 4, corresponding to the nodes 1, 2, 3, 4. Okay? So, actually, to make it more precise for you, if I can, it is not letting me do the text box here. Sorry, if I could have done it, then yeah. So if I do 1, give me a second. One more time with feeling. There you go. So this is node 1. I'm just putting it that way there is no confusion, right? That's node 1. That is node 2. Okay, got it. And so on, right? Let me now go back to presentation mode. So these are 1, 2, 3, and 4. Same thing, 1, 2, 3, and 4 like that. So you're drawing the adjacency matrix, right? I put them in the wrong slide, but it's in the previous slide. Sorry about that. Okay. So this is 1, 2, 3, and 4, 1, 2, and 3, and 4. 1, 1, 2, 2, 3, 3, 4, 4 have 1s there diagonally as per how Aij is equal to 1 and 0 are defined. And then whenever there's an edge, you put a 1. So from 1 to 2, there's an edge, you put a 1. 1 to 3, there's no edge, you put a 0. 1 to 4, there's no edge, you put a 0. So this is A represents the adjacency matrix for this figure. Now A star, which is the transitive closure, you see you get all 1s. How did you get 1s there? Because, okay, 1 to 2 there's a 1 because there's an edge. Now can you now come from 1 to 2 to 1 to 3? Is there a path from 1 to 3? That's what we are capturing, all the paths, right? Yeah, there's a path from 1 to 3. The way you go there is 1 to 2, 2 to 4, 4 to 3. So you put a 1 there. Is there a path to 4 from 1? So yeah, 1, 2, and 4. You put a 1 there. Now you come to node 2. Okay? Is there a path from 2 to 1? There is no path. You put a 0. 2 to 2 is 1 by definition. 2 to 3, is there a path from 2 to 3? Yes. You go from 2 to 4 to 3. You put a 1. 2 to 4, obviously, there's a path, you put a 1. So that is how you come up with a transitive closure. This is a legitimate question, by the way, for you. Because what they tell me is, as long as there are paths, then I'm good. If there's no path, then you cannot traverse all of them, right? So you have to cover all the vertices. So as long as you're able to do it, then you're good. Okay. Now there's this guy called, there's an algorithm called Warshall's. Let me make this one small so that way you can see it. So there is Warshall's algorithm for transitive closure, where you are able to basically compute the transitive closure for a given graph. Okay. Looking at it in another way, it's basically nothing but all paths in a directed graph. So you can see the graph given. I have some difficulty today. Give me a second. So you can see the graph given on the left, right? So you compute the transitive closure for all that. Okay? And then as long as there are paths, then you fill out, and then you get the transitive closure. Okay? Give me a second. What's the main idea here? The main idea is as long you are going to see if there's a path between two vertices, if there's an edge from I to j, meaning direct edge, or there's a path from I to j going through some other vertex. Okay? That's vertex 1, vertex 2, and so on. That's the main idea there. Okay? Now we use these things in what is known as dynamic programming. I have not introduced some dynamic programming for you in this class. You have to wait till my next class to see that. That's where we get into some greedy algorithms and so on. Okay, that is where we use it. I don't have to cover this slide, but it is there for those of you who want to know more about it. Okay. Okay, I'll skip that because those are all some advanced stuff there. So it shows all the analysis of how these things are done using Warshall's algorithm. You can ignore these slides, okay? Now you will revisit this all pair shortest path, okay? So all we are doing here is, one second, I should have verified this. Okay, this is good. So what is the all pair shortest path? It's a graph that has most optimal list of vertices connecting any two vertices that can reach each other, okay? Somehow my things are not wrong. Okay, there it is, okay? So if you look at the graph given here, you are looking at all pairs, right? 1 and 5 are already connected, 2, 1, 4, 2, these are all connected, right? See the color-coded one here, okay? So from 2 to 1 to 5 you can go. That means you are looking from 2 to 5, all pairs, right? Same thing from 8 to 6 to 3 you can go. 7 plus 8 to 7 through 8 to 6 you can go. 7 through 8 to 6 to 3 you can go. So these are all the various paths that exist where you can traverse from one node to each of the other nodes. Okay, that's what the all pair shortest path is. Okay, so it draws that. Okay, so then there's a usage for where do we use all of these things, right? See that big satellite communications. Okay, even in the medical field, you get those things. Airline routes, you get those things. Because that is the whole idea, right? Because they may not be a direct path. It's like routing an airline. Like if you look at in USA or even there in India, you have this Indigo flights, right? Indigo are those cheap airline flights. In the morning, they start, let's say, in Vizag. Okay? And then they go from Vizag to Rajahmundry or maybe Rajahmundry to Hyderabad, Hyderabad to Bombay, Chennai. They route that flight to reach by night time some destination. And the trick is how to route them, right? The way you do that is you find these transitive closures and then all pairs distances. Using that intelligence, you apply the algorithms like the Dijkstra's or Kruskal or Prim and so on to come up with an optimal route. Why you need an optimal route? Because you want to save money on fuel, right? Fuel is a very expensive stuff. Okay. Now, oftentimes you would think that it's all about saving fuel and cost, right? It's not just that. What I call it as, from a practical application viewpoint, what is it that you're trying to optimize? Okay. Cost is not always the optimization factor. You should not be under the impression. Typically, cost is, but sometimes time is what we want to optimize, right? It's like what I would call it as, like if you go on highway, let's say if you go on highway, like you have all the ring roads in Hyderabad, okay, outer ring road, inner ring road, and so on. If I go on highway to the airport from my home in Hyderabad, it adds about 25-30 miles more to the airport. Actually, even 40 miles, I think. However, it's also going to save me 1 hour time because there are no traffic lights and so on. So I want to optimize time, then I would take a longer route where I'm actually spending more time on gas. Gas means petrol. In the US, we call it gas, right? So depending on the optimization factor, you can choose the right path. And the way to do that is to understand the concept of transitive closures and all pair shortest paths. Okay. So I gave an algorithm here again. Only the concept needs to be taught, but for those of you who want to trace, I like tracing. I know you know that, right? I want to look at the algorithm. I want to trace with test data. So I gave some stuff here for you to look at after the class. Okay. That's pretty much it. If you look at the syllabus here, let me see if I can bring up the syllabus here somehow. File open, bear with me for a second. Somewhere here in somewhere here I have to open. Unit 6, part 1 name maybe. Yeah. So if you look at the syllabus here for this one, these are like, basically this chapter is meant to give you concepts, not too deep, right? We looked at the basic concepts of graphs. We know how to represent the graphs using linked list and adjacency matrix. We talked about that. We looked at some what breadth first and depth first traversals are. We looked at how to calculate the shortest paths, and I gave you the algorithm there that you have to convince yourself. I gave you the what transitive closure means and what minimum spanning tree means. And then those couple of algorithms there. I didn't ask for Kruskal, but he won't discuss just prim without discussing Kruskal. Okay? Again, it's only concepts, no programming required. Cool, right? That completes the syllabus. Okay. I will put some notes on Unit 6, not matrices, not like PowerPoints. I'll put some PDF documents for Unit 6 as well, so which can act as a cheat sheet for you for your finals. Now, when I say cheat sheet doesn't mean you take that sheet and cheat there, okay? And that's just a common term that we use here. Some notes for you to, for helping you prepare for the final. Okay. Questions, comments? Let me pause here. I've been talking too much non-stop. We are pretty much done with the syllabus. What is the time? It's almost time, huh? Wow. So what I want you to do is, after I post this one, remember there's some examples that I gave you. I said, hey, I want you to trace those things. So before we have our next class, go through these slides, trace, okay? Do the traces on the example that I gave you, and next class when you come, you ask me questions, okay? What else will we do next class? I'll email to you how the next class is going to go, but at the outset, go through all of your units, and each of you, I want you to prepare about 10 questions. There's a process that I use. I'll explain them in the email in detail. Each student, for each chapter or unit, whatever you want to call, what are the top 3 or 4 questions that are relevant to the chapter is what I want you to write. Even if you write about 2 or 3 questions per chapter, which are important questions, like 6 units means you will get 18 questions. Okay? Now those 18 questions, right? If you know the answers to those 18 questions, then you are in good shape for the final. Okay? And then when I review next class, I'll do the same thing like what I'm asking you to do. I'll say, hey, what are the 3 big takeaways for each of these units? Okay? And I will simply focus on reviewing those big 3 takeaways in the next class. Okay? And hopefully those things would match your questions too. So between those 2, you should be in good shape to excel in your final exam. Okay? I'm going to send you a detailed mail one more time in summary. Go through each of the units and pick the top 3 things. I mean, if it is 4, it doesn't matter, okay? What are the top 3 or 4 questions? Do it in groups of 2 because you learn faster when you do it as a group. Okay, everyone understands what I'm asking you to do before next class? Are there any questions? Faculty members, do you have any questions? Now, when I do review, I would be seeking help from students and faculty to review some of the material in the next class. So be prepared, make sure your audio is working, and it is working good without static. That's all, folks. Nothing more to add today. Sorry, we did not do too many exercises other than the first one, because these are all basically tracing the algorithms which you can do on your own. Okay? And if you have any questions, just shoot me an email before next class too. Done. Any questions? If not, I will sign off. Have a fabulous day. Happy Navaratris.